Hello, this video is about the trigonometric multiple regression analysis. You can also call it spectral analysis. This is for time series data, especially when the data presents cyclical patterns, and we would like to estimate how much the variable time itself impact the variation of the response variable. So I have a discharge data here starting from January 1st, 2001 to December 31st, 2007. So let's run the data, let's see it. So we have the columns here from soil moisture, soil temperature, air temperature, ET. These are the abbreviations: SM, ST, AT for air temperature, ET for evapotranspiration, SH for soil specific humidity, P for precipitation, and D for river discharge. This is how I created the data. So let's plot and see it, explore the data. So this is a pictorial view. Have our D, which is the target, the river discharge here, and the relationship with P is just about here, not clear in terms of linearity. Seems something with specific humidity. You can draw a line here and see, like there is increase of discharge with increased specific humidity, kind of. With evapotranspiration, what you see here, with air temperature and the soil temperature, we have opposite direction, decrease of discharge with higher temperature of air and soil. With soil moisture, we can draw a line here and see what's increased. But we need a time series plot to see. So I transform the data into time series. So my data equal TS discharge. So discharge here. So TS transform it, and then I plot my data. It's going to give us time series plot. So this is the time series plot. Okay, we have time here, x-axis, from January 2001 to December 2007. We have 84 months, right? 12 times 7, 84. So that's why we have this here. So month 1 to month 84, and our target is here. And you see the pattern is cyclical. It's repeated, like every year have repetition. This repetition is because the data is from the monsoon region, so the region where the climate is impacted by the monsoon. So we have rainy season and dry season. Rainy season versus dry season, hot season versus cold season. So it's a cycle. That's why we need to assess the impact of the time itself. And since we see here that we have the kind of sine and cosine function, we use the trigonometric regression. We use the sine for the time. We have the period 2 times pi t, then the cosine with the same. This cosine function at the same time, and this we develop it, and it's going to give us an idea about how much the time itself impact the outcome. in addition to precipitation, specific humidity, ET, air, soil temperature, and soil moisture. So in this case, we cannot ignore the time. The impact, time has an impact. We have the highest values of discharge here and the lowest values of discharge here. So the pattern of rainy season, dry season, rainy season, dry season impact the response variable, the variation of this response variable. If we take the temperatures, air and the soil, we see two peaks. So in this region, we have March, from March to April, April, probably until May, highest temperatures, and then it decrease to August, September, there is increase of temperature around probably November, and then decrease December, January. So hot, cold season. So when we take precipitation here, because the river discharge depends also on precipitation. So we see here the highest, the same thing here, the pattern, precipitation, highest values and the lowest values. So rainy season, dry season, and then you see there is time delay between where the precipitation is the highest and where the river discharge is the highest. That's why we need to use the trigonometric multiple regression analysis. So the question 1, as we see the patterns, would be is to what extent is the variable time predictive of the response variable? In our case here is river discharge. You may have another type of data, but this variation or rainy season, dry season, how much does it impact our outcome? And then we try to answer another question: to what extent are all other variables combined predictive of the response variable? So we take time only, we quantify its impact, and then we put all the other variables together, including the residual of time, and assess their impact. And then we try to answer the question: which variables give us the best model? So we are going to go through it one by one. Let's see. So we'll have several models here, and we pick the best model: time-based model, all based model, all time-based model, all variables-based model, and which one is the best model. Okay, let's continue. So we have we set the seed to reproduce it. Already installed the packages. Let's just call the libraries ISL, R, and mass. And the time I said 84 months. So we create a vector. I created vectors here instead of taking the whole data set. I selected some variables. So T equal C 1 to 84 gives us 84 months for our time, and this is here, and the length of T, to make sure that all the variables have the same length. Otherwise you may not be able to run it if the length differ. So D equals C. I just copy the values and paste here. D equals C. I open the parentheses and I copy the values of discharge from the column and I paste it here, and I separate the values with commas. So and the length of D 84. I did the same for precipitation. I copy P equals C, parentheses, copy the values from the CSV file and I paste it here, separated them with commas. And the length, and we did the same for soil moisture. length 84. I did the same for ET, length of ET. I did the same for specific humidity, and the length of specific humidity 84, and I took the soil temperature and its length 84. So all of them have 84. I didn't take air temperature. They have almost same values with soil temperature, and they might be highly correlated because the model assumptions, so we have to deal with multicollinearity. But just to make it short, very short video, we may have more variables than this. Okay, now question 1. To what extent is the variable time predictive for river discharge? So we want to assess the importance of the variable time in predicting the response variable. So we have T, 1 to equals C, 1 to 84. We plot our T in a discharge, type L, X lab, X label is time, unit is month, Y label is discharge, unit is cubic meter per second, point character 20. One more thing I added here, which is important, is the Y limits. So I put the limits in between minus 500 to 1200 because of the fitted values that go below the 0. Yep. Below 0, they go below 0. There are some negatives here. So let me run it. So time in months, Y label, discharge, X label, discharge, and Y labels is cubic meter per second. So this is the observed discharge. And now we have Y dot time. This is the time-based model. Equal LM D for discharge, the sine of 2 times pi times 12 divided times t divided by 12, plus cosine of 2 times pi times t divided by 12. This is the form of our trigonometric regression. Why we divide by 12? Because of the 12 months. We have monthly data, so 12 months in the year. So our period t equals 12. So 2 pi t. If you had the daily data, you would have divided by 365. If you had weekly data, you would have divided by 52. Since it's monthly, we divide by 12. So you run, and you have the summary of Y time. So cosine function, sine function, cosine function, they intersect with the p-values. Everything is fine in terms of significance, and the function explained point is 77.68% of the variation of river discharge, so pretty high. But we need to go more than that, take the residual of this as the variable time itself. So based on this, we can say that we reject the null hypothesis, because with the statistical significance shown here for the p-values, the variable time does significantly contribute to the changes of river discharge. So we cannot ignore it. We cannot say that time, the fluctuation, or the changes of the seasons here doesn't impact too much our outcome or response variable. And then consider only the climate variables for the analysis. So we need to include time. So here we plot the fitted values of the time-based model, points, parenthesis t, fitted, parenthesis y dot time, type L, color blue. This is for fitted. And then we plot the residuals
points T y dot times dollar residuals type L color red. So that's the difference between actual and predicted. And then legend, you put at the bottom, you put a vector observe, fit it in residuals, and a column for black, blue colors. Sorry, black, blue, and red for observe. Predicted and the residuals. Line type C11, horizontal true, the boundary type no. So we run the legend, and this is what we get. This is our time-based model. Only time. The sine function, sine cosine function. These are these. Okay, so now the question 2. To what extent are other variables predicted for river discharge? So now we need to build a model including the residual of our time-based model. This is residual. We have a residual here. Yep, this residual. We include the residual. It's here. We add all the variables we have, and we first plot time and discharge again, and we respect everything the same. We can change probably the whiling here, because the values of the predicted this time may not be the same, but I kept everything. Y lab is discharge, X lab is time, so the same thing. So y dot all, so all variable space model equal ln linear model discharge delta soil moisture plus precipitation plus temperature plus ET plus ET is evapotranspiration plus specific humidity plus residual of time. We include it here. This represents the time itself. You don't deal now with cosine and sine of time, but the residual of the time based model. Sorry, I should not select run it. So okay, we run all the model, and summary y all. This is what you get. All the variables are statistically significant except for ET. So the R square is 95.74%, and the p-value statistically significant. We do the same. We plot the fitted values for y dot all point fitted y dot all type L color blue. I kept everything the same colors. Black for the dark is for observe, blue for predicted, and the red for residuals. So you run, these are the predicted. You run the next line code is the residuals, and this code gives us the legend. So we can see here, compared to the previous plot, this one is pretty close. We predicted and observe for the highest values. This is for the rainy season. The patterns are almost the same, although they don't here pretty good. But for the dry seasons, they don't really follow very much. So it gives an idea about how many models you need to build here. Do you need to build a model for the whole year, or do you need to build a model per season, rainy season and dry season? So yeah, you explore your data based on this. So now that we have this column of p-values for all base model, we sort these p-values. So we sort the variables based on their p-values, starting with the lowest to the highest. So we see here that residual and the precipitation have the same, but we need normally to start with p. So p is the lowest, because whatever we do, we have to add the residual. Residual represents the time itself. So, and then comes the soil temperature, then comes the soil moisture, then the specific humidity, and then ET. So if I'm not misled, if I did not make any mistake, this is the order. So the lowest is p-value, and the highest is the lowest is p-value is precipitation for precipitation, and the highest p-value is for ET. So the next step, you already answered the first question. You know the function, the sine function of time gives us about 75% of the variability. Explain about 77% of the variability of river discharge. When we put all the variables together, it gives us about say 96% of the variability of river discharge. Now, how to find the best model? Which one is best? For this, you have to build models of increasing complexity, starting with the residuals from the time-based model, and then add the independent variables starting from the one that has the lowest p-value. So here it means that our first model would be based on residual. Second model will add to residual precipitation, and the third model is going to be residual plus precipitation plus soil temperature, and so on. So why do we add residuals? Residuals from the time-based prediction estimate the degree of impact from adding the variable time on the outcome. So basically, the residual from the time-based model, which is a function of sine and cosine, gives us the impact of adding time on the outcome, on the response variable, basically. And then at the end, when we build first and the second model, you have to perform ANOVA, analysis of variance, to compare the models, and so on, and we continue until we get to our conclusion. So model 1, we take residuals as predictor, only residuals. So we have the same code here, plot D, plot parenthesis T, comma D, comma type equal L, X label time, and Y label discharge with their units, and everything is pretty much the same. And this time we go to minus 700 because it goes more than that. So out here, then y dot complex 1, that's what I call complex models, or model of increasing complexity. So you'd have y dot complex 1 to y dot complex 2 and so on to the last model. So y dot complex 1 equal lm discharge based on resid of t. So the residual from the time-based model. And then you see the summary. Pretty much. So the time here itself is plain about 21% of the variability of the discharge. So it's pretty good, 20%, 21%. The variability of the discharge is explained by time. And then explained by the variation of season. Rainy season, dry season. That's a lot. You cannot ignore time here. So the first, that's a lot here. You cannot ignore time here. Look, 21% of the variability of discharge is explained by the variation of time. Okay, p-values, not bad. Statistically significant. I'm sorry. Then we plot the fitted of y complex 1. Points, parentheses, t, fitted y dot complex 1, type, color blue. Then points t, y dot complex 1, residuals, color red. Let's zoom and see it. So 20% explained by the variation of time. This is the plot. So the next model we added to the result of time precipitation. The plot's the same for first line of code. Y dot complex 2 equal lm d tilde result plus p. We run. Then we run the summary of our model 2. So now the R square is about 30%, so 29 to 21 to about 30%. And the P also is significant here. P value to that. And we plot for the fitted values of the model 2, we plot, and the residuals of the model 2, we plot. And we see here so we are going progressively there. So we run the ANOVA between model 1 and model 2. And you see, tells us the model 2 is better than model 1. Then we add the third variables that has the second variable that has the second climate variable that has the lowest p-value, which is ST. So the code to run the plots is still the same. Y lim minus 500 this time. The Y limit is just to adjust this Y component here. Where should the plots here go? If it goes below than that, you have to increase. Yeah, we do it here. So we reduce normally. Minus 700 is below minus 500. So on. So we stop at 500 minus 500.
still for the model 2, model 3 is spent about 78%, so from about 20 to 29 to 78. So we are still continuing. Residual plus precipitation plus soil temperature is 0.78. Residual is about 20. Residual plus precipitation is about 29. And now you plot the fitted for the model 3. Complex model 3. This is getting closer, right? And then we plot the residuals using this code. And then we plot the legend. So it means we're really close to our best model, but you have to build and continue. It's like increasing complexity, so until we get to the closest result. Y all gives us about 96, so we are at 78. So now we run the ANOVA between the three complex models. So model 3 and model 2 equivalent here. We continue, we add our third variable, which is soil moisture. Third climate variables, but in the model is the fourth variable. So the 4 are predictors. Model 4. Same thing, we plot time and the discharge. And our y dot complex 4 equal ln d delta resit plus p plus st plus sm. And we run it. The summary model, we are at 93. When we add sm, the p-value for st decreases, but they are statistically significant. The p-value here is statistically significant, and the r square 93%. We are getting close. So we plot the fitted for model 4, we plot the residuals for model 4, and we put the legend and we compare. We are getting closer. Seeing the plots here. Observe, fitted, and the residuals. Getting really close. You can even stop here. Depending on what we need, especially on our knowledge of what's going on the ground. 95, 93. Okay, now the ANOVA, what's going to tell us for which one is the best. Okay, when we add soil moisture, based on the p-values, all the two are statistically significant, the 3. Then we go to model 5, we add the soil, the specific humidity to the previous variables. Our plot is still the same. Time is on X labels and Y on discharge on Y labels. So discharge versus time, Y versus X. So complex Y dot complex 5 equal ln d resit plus p plus st plus sm plus sh. This model 5. And the summary of our model 5, 95.72. P-value statistically significant. We plot our fitted
for model 5 and the residual for model 5, and we put the legend. We run everything and we see the plots. Pretty good. This is for the rainy season. We see here, very good, very good, very good. For the dry season, they don't really follow very well. So as I said before, it can help make a decision. So now we run down over the 5 models. In terms of p-value, this one is a little bit higher, but it starts considering come down. Those are equal. Now we add our last variable, which is evapotranspiration, to the model. We plot our discharge versus time. Then model 6, it is added. Then we run the summary. Summary of model 6. Oh, it is not good. It is not good. Okay. Precipitation is low. After that comes ST. Yeah. After that comes soil moisture. Then SH, then ET. If I am not wrong, okay, 95.74, which doesn't change too much compared to the previous one, which was 95.72, I think. Yes, very close. So that plot the fit it for the model 6 and the residual for model 6. Put the legend. Pretty good. Okay. And the ANOVA model 6 is not good. Model 5. What is the model 5? Model 6 because we have ET. Model 5 SM and SH. P-value increased here. We have also our F statistics we have to consider. So normally is model 4. Yeah, because I didn't consider air temperature, so we stopped here with ET. So when you analyze this, model 4 is the best. So model including. So the best variables to predict our river discharge, in addition to the variation of time, are precipitation, soil temperature, and soil moisture. Well, this is for geoscientists. They know the importance of soil temperature and the discharge, the importance of precipitation on the river discharge, the importance of soil moisture on the river discharge. And if you are from the monsoon region, you know that precipitation is the rainfall governs everything. Okay, the soil, the moisture in this area we know about is about precipitations. The rainfall governs the soil moisture, governs the soil temperature, it governs the river discharge. With the impact of climate change, we clearly see things. So normally Y base is LM, date,
delta P plus ST plus Sn. But I consider some reasons to take precipitation and soil moisture as the best variables instead of soil temperature. That's for my personal reasons in to not make the video longer. So you can consider it 3. It's up to you depending on your area of study. So first, make for practical reasons. I made that decision. So we need now to make figures to show the raw data versus predictions of the purely temporal model and the best model. Purely temporal model is this plot. It's the same plot, it doesn't change. So we have discharge versus time. Y time, you already said it, equal Sm, Lm. D delta sine of 2 times pi times t divided by 12 plus cosine of 2 times pi times t divided by 12. This is our trigonometric regression, and then we put the fitted. I omitted the residuals here, so fitted, predicted, and fitted. This is for our time-based model. And then come to the best model. The best model, I took precipitation and the soil temperature in addition to residuals. But you can put the SC here as well, it doesn't change. So like this. Okay. And we have a summary of wave base 92. Let's add ST and C for wave base. Sn plus ST plus P, residual of T plus P plus ST plus Sn. Gives us 93. So even the values don't point too much, but it's pretty good to consider. 92.14% and 92.01. About 1% increased, and then let me take P plus Sn, and I will come back to it, and then we fit it. Observe temporal and the best model. Fitted for best. So Y best and the fitted for Y best. And we put the label. Okay, so observe this river discharge, temporal river discharge, and the best model. Okay, best model, take precipitation plus soil moisture. What if I add the ST? What's it going to give us? So soil temperature plus soil moisture as ST as best variables. Okay, we know already that gives us about 1% more. It's less than 9%, 93.9. Let's see. It was how many? 92.14. Oh, 0.13. So it's less than 1%. 87.87%. Okay, it doesn't change too much. So that's why I say, okay, I can consider only soil moisture. Soil moisture is much more important than soil temperature in
this region for some agricultural activities. Also air soil temperature, but the soil temperature depends on the insolation. So the air temperature, soil temperature are highly correlated in that region. So that's why I drop it. So let's see what's going to be the impact on the plot. Not much. So okay, I remove the SC. You can keep it, but the idea is clear here. You need to assess the impact of time. You have time series data. You have a cyclical pattern of your variables, and you know that your variables depend on the changes of seasons: rainy, dry season versus rainy versus dry season, cold versus hot season. So it means that your outcome is also a function of time. It's not, in my case here, I deal with the monsoon system. So you have rainy season, dry season. In your area, you may have the winter, the spring, the summer, and the fall system. So all these patterns, all these seasons have their patterns, and the patterns impacts the phenology of everything you are doing, impacts all the activities you are doing. So when you deal with the environmental data, you have to, specifically time series analysis, you have to deal with these variations of seasons. And then when you deal with that, you perform the trigonometric regression that helps you to assess how much time itself impacts the changes of your response variable, in addition to the climate variables you have. So, and as we see here in this, can we say that a model is enough for all the let's see, okay, oh sorry, can we say that a model is enough for all the 12 months of the year, for all the seasons, or do you need more than one model for the year, knowing that within the year we have seasons? So in our case here, for the rainy season, the highest values, they pretty much go together. Here, all the patterns are almost the same. Although they don't really much here. But we see for the rainy season, it's not a big deal, but for the dry season, there is problem. There's problem. So my conclusion is that we cannot say that you have one model for all the 12 months of the year. But we need more than a model. A model for the rainy season, another model for the dry season. The dry season, definitely we need another model for it. And probably need also to see within the dry season there are some regions, some months which are very hot, and other months that are very cold. So it gives an idea about how to explore your data. So, and in addition to that, you need to make sure that the model assumptions are met. I didn't consider that here. And you need to split your data into training and testing data set, and also run the cross validation. I didn't do these things here because my focus is on showing how to impact the how to assess the impact of time. It's important when you deal with cyclical patterns. So the trigonometric regression helps to find out, as we have seen it here, to find how the variable time impacts
the response variable from by using the sine function of time. So thank you for watching this video. See you next time. I hope it helps you.